And today we're going to be looking at the state monad. We're going to be doing this in order to add variables into our language. So the state monad is quite an exciting monad. It's not like any other monad you've seen before, and I'll show you why. So let's define, okay, so data state A. We need two variables for this. We'll do it like that. State MA, so we have two parameters in this type, equals, and then I'm going to use record syntax. I don't know, I'm sure I must have shown you record syntax, but I'll go over it again anyway. Run state, and it's going to be of type M to AM. So that is the data type. So first of all, this record syntax, in case I haven't shown it to you, say I was making a database and I had a person type. I might say that the person has an age, which is an integer, a name, which is a string. What else could a person have? A date of birth, which would be another string. They might have an ID, which is an int. And this type is wholly useless to me because I'll never remember which string is which and which int is which. And, you know, these can get really long. You've seen incredibly long structs in C maybe, or classes with loads and loads and loads of method variables. So Haskell has this thing called record syntax, where instead I'd say age. Let me just get the brackets how I like them to start with. There we go. Age, name, like this. What was it? ID of type int. And then date of birth, which is type int, string. So that would be the record syntax version. And what this does is it defines, first of all, person, exactly the same as before. So this is the same as writing person, int, string, int, string. I know I had it in a different order last time. But it also defines these functions. And age takes a person and returns an integer. Name takes a person and returns a string. So this record syntax is really useful for sort of implicitly defining functions. And here we have one. Run state is of type M to tuple AM. I don't think I need these outside brackets. I like to use as few brackets as possible. Good. So this is the first time I've made a type. Oh, look, I have forgotten something. I need to give it a constructor. Maybe just st. Good. So it's the first time I've given you a data type that has a function inside it. Normally it's just values, but this time we have a function. And what I'm going to do, I'm going to go through and I'm going to define how this is a functor first, then applicative, then monad. It surprises people when they first see sort of a function type that it could be a monad, but it definitely is. So, instance functor. Now it's going to be state M. The reason for this, the reason I have here M, you notice up here I just had ID, and that's because I can't remember how they write it, but sort of a functor, I think the definition of a functor is, in fact we should be able to check, this will error, but cable REPL, I wonder if it writes it like that here. Come on, I know you're going to break. Oh, thought so. Info functor. Yeah. So here it's sort of given us a type alias for what a functor is. I don't think you defined this, but it doesn't matter. We're going to go later into what this kind of notation means, but essentially a functor. So this is a kind notation, okay? And And just like values have types, types have kinds. And these stars, they represent... so these stars represent types. That's what they represent. And a constraint represents something like a type class. So when I say f is a functor, I write functor f. Functor in that setting is a constraint. And that makes sense. I type functor and then f, and what I get back is a constraint, where in the type, f is always got to be a functor. But anyway, it doesn't matter. Functors always map types to types. That's more the point of this exercise. Doesn't matter if you didn't understand that. Doesn't matter. Cool. So, instance functor state m where. And now these definitions get a little bit tricky. So fmap, and then we got our function type, and then we have, and there's almost no point, state f. Okay, so we've pattern matched. Oh, I've got f twice. X, I know it's a function, but we're going to call it x. So what we have to do is we have to think about what we are going to return. So writing out the types in these really matters to help you. So fmap is of type a to b to fa to fb. And of course I need to say functor f. Okay, so here we have our a to b, here we have our fa, and now we need to return something of type fb. So the way to go about this is to reconstruct state. So we're going to say state, and then inside there first of all needs to be a lambda, because we're going to sort of remap the memory. Shouldn't call it that. M. So because the only input to, it's st. I changed that, sorry. st, get the constructors right. So because st, the constructor, has one input of type m to am, we're sort of using a lambda to get the m. Right then, so x is of type this. And what we're going to do is we're going to say let, we'll call it a m prime equals xm. Okay, and that is going to give us this back, am. In, now I'm going to do the in on a new line. Whoops. In, and that's going to be, yeah. Do I need to do that at all? No. Oh yeah, I do. In f a m prime. So I hope that made sense. You can kind of see how the types match up. So this constructor takes something of the type this. So I give it a lambda. So now I have this bit done. And then I essentially shoehorn the rest just to get the types to fit. And of course apply that important f to that important a. Great. So I'll take away this type. Next, let me mute my phone. Okay. So next we need to go instance applicative of state m, where. So pure x is pretty easy. That's like this. You can, oh, what am I doing? You can see how that works. I don't think that needs much in the way of explanation. The next one's pretty tricky in comparison. So we have f applied to x. So let's do some pattern matching. So state f applied to state x. So what we're going to want to do, I've really got to think about this. Okay, the answer is going to be like this. And I can grab myself that important lambda. So we'll get the function first. So I'll say let f prime m prime equal fm. Okay, and then not yet, fm in, and we're going to do another let's x prime and m prime prime. No, that looks nicer. Equal x m prime in, and then it's going to be f prime x prime m prime prime. Yeah, that looks like it's it. It's quite hard to explain these ones. And I'm sure I will have made a mistake somewhere. Let's check. Have I made any mistakes? Of course. Oh no, this is... oh, that's a mistake from... Not a mistake, that's a problem with... hold on. Set dash x flexible instances. I think you might remember that. There we go, that's better. Oh look, that's a typo there. 29. There's your typo. Hey, we're doing okay so far. Finally, monad, instance, applicative. No, what am I doing? Monad. And then state m, where. And so we have to do bind now. So this, by the way, this is a really important function we're defining. State monad with bind. I'm gonna drop a bombshell on you soon. St xm bound to f equals. So again, we start with that lambda, and what we're going to do is we're going to extract the values we need. So let x m prime equal xmm, and then I think we can do this on the new line, in, and then we want f of x. So that's going to, and we need to do, where does the m prime come into this again? Let me work this out. So we've extracted oh yes, so f, if you remember the type, f is of type A to MB, which is kind of the same. I'm going to remove the constructor of A to, and then it's going to be M to it's kind of like that with sort of a state thing inserted here. So we've given it the A and we get this back. Anyway, onwards. I know that isn't it though, because I need to use the M prime somewhere. Oh, I know where. Oh, I'm so stupid. Because we're inside the lambda, this whole thing at the moment is kind of like M2 state whatever, MA. So I need to change this. I need to basically get rid of this. So what I'm going to do is I'm going to change that to the in there. And I'm going to say let state f equal fx. No, that's not going to be an f. I'm so bad at coming up with these variable names. State g, there we go. In, and then, so we have g now, and I'm just going to apply m prime to it. That should be all. Let's see. Yes. Okay. So we've defined the state monad. It is a matter of just getting the types to fit. It really is. And don't worry if you didn't quite follow, because you almost never define these things yourself. You almost always use, I think MTL is the library. It's really useful. I rarely go and derive these things from first principles because I don't derive them with all of the performance enhancements that library contains. So what have we done? That's kind of the first question. We've made a monad. And I'm gonna completely ignore the constructor for now. Let's just pretend that state MA is a type alias for this. Let's pretend that for now. We've made a monad which essentially allows us to carry state through functions. And if you kind of look at the types, it'll make sense. So if I said m or state, if I had state xm and I bound that to a function, let's look at these types. And I'm going to try, I kind of know how I'm going to explain this. So pretending everything's a type alias so that we don't have to worry about the constructor, xm is of type m to a m, okay? And we bind that, I'm so sorry for this complete abuse of syntax, to something of type a to m to b m, if you like. And our result, in the end, becomes something of type m to b m. Now, what I'm going to say is that essentially some of these m's aren't, I mean, they're the same type, but they're not the same value. So because this is a function, when this function is run, that m and that m are probably going to be different. But essentially, if I mark this one and I mark that one, and then this is a different one, and then you have that intermediate one. It might make a little bit more sense in that we have this monad. I mean, it is a function, this value xm. It is a function from memory to some computation. It represents a computation, if you like. And it has a state of memory. It has how the memory was before the computation was run. And then we have a function on that suspended computation. And when we bind them together, we essentially join them into a new suspended computation, or thunk, which just joins them together. It assumes the same initial state of memory, and it gives back a different end state of memory when we link them together. So the reason I'm saying this is because I'd like to say that essentially we've seen the data type IOA, and essentially that is state, okay, and then we need what's our sort of memory type. Real world is what it's called inside Haskell. So that is the definition of the state monad in Haskell. So your programs, do we have a main in this? I don't think we do, actually. Oh, we do. So programs in Haskell are of type IO this, which is essentially the type state real world and then unit. And we can pretty much ignore unit. And that is kind of the same as the type real world to I can't remember which one hold on. I can't remember. Value first. Yep. Real world to real world. And we can basically ignore unit. It doesn't really add any information. It just adds structure. It allows us to have intermediate values. And so remember when I said a program just mapped a list of inputs to a list of outputs? Not a list of inputs, but some input to some output. Well, in Haskell, when your program uses I/O, it maps your program from the state of the universe before you write your software to the state of the universe after you write your software. That's how it works. That's how it gets around things like, so say I had a function, has the user clicked this button. Well, now you know that I/O is a function from the state of the real world. You can see two things. First of all, that function is still pure, because say I found a universe state where I wasn't going to click the button, and I passed that in repeatedly, that function would always return false. And say I found a state of the universe where my user was always going to click the button, and I passed that into the function. I know it makes very little sense. You have to be quite philosophical about this. Then yes, of course it would always return true. So this state monad, but with the real world instead of some area of memory, allows us to have completely pure I/O. And that's quite incredible. Now, I'll tell you, I was saying that bind here, when we use bind in our definition of main, where is it? Did I get rid of my... I got rid of it. Made no sense anyway. When we use bind, essentially what we're doing is we're adding all of these intermediate functions which map the real world to something, and we chain them together so that we end up with one unevaluated function that will map a state of the universe to another state of the universe. And when we run that function, that is, when we run that program, that's the same as giving it the state of the universe. And the program goes and it might change things about the universe. You know, if it's printing something on your screen, that is a change to something about the universe. And at the end, it returns the new version of the universe, along with any changes it makes. So it's incredibly mathematical, incredibly philosophical, and a bit of a cheat, I'll be honest, because the real world type, I believe, is changed at compile time to unit. And the reason it's there is to stop the programmer from being able to do certain things. And there's good reason for that. It means that if you go and you consider the correctness of your software, you still can, you can kind of assume that the real world is in your code, because your code will behave like that with the limitations Haskell applies. So it means that it's very easy to prove the correctness of your code. You don't have to worry about state because of it, even though it doesn't make it into your end compiled code. But I'm working on a project over a long period of time that's supposed to change that and actually put the real world data type into your program. And this has got applications, I think, to embedded computing. But I'm not going to talk about that. If you want to hear more about that, leave something in the comments. God, this video is getting unwieldy. So all we've done so far is we've defined the state monad. So let's add that to our code. So I'm going to change out the last monad we had, and I'm going to call it state and then mem. So mem, I need to get rid of that. Mem, I'm just going to define as a list of values. I've got my reasons for that. We'll see how far that gets us. And of course, I need to go everywhere I've used left, because we're no longer using that. I'm going to put error back. I don't know if there is anywhere else, and I need to add in these get out of jail free cards. So I don't like this as much. I like having monad fail, but doesn't matter what I like, does it? Right, so let's see if I've made any hideous mistakes. Yes. So expecting one more argument to m value. Oh, these are not errors that I like. Did I change? Oh, for a start, let me define that properly. There we go. Okay. You know you're a Haskell programmer when you see it says 65 and 90, and you realize it's going to be none of those things. Okay, so that was a success. If you minus all of my talking time, that really didn't take long to change the interpreter to use the state monad. And of course, we've gained nothing. Eval. Well, we've gained something, I guess. So here it says no instance for... I need to give it the... Yep. And we still have a no instance. So if I say let res equal this, the type of res is m value or state value. But that's okay because I have that function run state. And I need to give it some memory, which is just the empty list. And there we go. And it's given us back the value and the state of the memory after we've done our computation. So let's add some variables. I think irritatingly I might have already used. Yeah, it's fine. Okay. So we're going to have two things. We're going to have one called new. And new is going to take in an expression. I think we shall see. Okay, and we're going to have dref, and that is going to take in an expression. So we have two new pieces of syntax here to do with variables. So let's find the end of our eval function and let's add these in. So eval new e and then env. By the way, if you look yourself into the reader monad, you can put env into the monad as well, so that your eval monad is just expression to m value. You can hide that as well, and then it was dref e env equals. So which of these is easier? I think I know. So do notation to date. So what we need to do is we need to say that, okay. So num val. So what E is going to be is it's going to resolve to just an integer offset in that memory list. That's the plan. So yes, so num val. Oh, I'm gonna have to add more to our expression. Anyway, I'm gonna stop chatting rubbish. Num val I for index is gonna be eval e in env, and then what we're going to do is we're going to return. So we need to be able to extract the state. So we're going to have to define two additional functions, get and set. So get is going to be of type state mm, and set is going to be of type a to state a unit. Okay. So what get does is it kind of takes whatever's in our memory and makes it the accessible value of the monad. So get is of type state, so we have to start with our constructor, and then m to that's it. That's get. It's a very easy function to write. It kind of feels weird that it works, but remember when we bind, we pass the memory in. We pass the memory all the way through. So whenever we run this in a monadic chain, it's going to have the memory of whatever came before it. So that's get, and then set. Set a, call it x, equals state, very easy one this, m to nothing x. So we kind of discard the memory. From these two, you can make a function modify. Let me just, you can make a function modify, which takes a function that changes the memory instead. But this tutorial's already getting too long. So, okay. So what we're going to do is we're going to get, and we're going to stick that into, we'll call it mem. So we've got the mem. Then we're going to say let result equal mem I. So that's for lists. So I'm saying get the ith element of mem. And then we're going to, we don't need set for this, do we? No. Well, I guess that's what we return, isn't it? because that is of type value. So I don't need this let result. I just need a return. Lovely. So that's that one done. This one next. Do. So in this one, I don't like this one so much. I feel like I should pass in, because I could pass in this kind of null value. No, I guess I know what I could do. I know what I could do for this one. So anyway, so it works. Do I want an expression there? You see, I've not thought this one through. No, I don't. Okay, I'm going to remove that expression from both there and here, because we all know I'd forget to do that. So new is going to be, so it's going to happen in a very similar way. Mem is going to be get, and the index we return is just going to be return length of mem. That's it. But I don't like this so much because I think if I called new twice, it would return the same index twice in a row because I've not popped anything into memory yet. So what I think I'm going to do is I'm going to add to value, I'm going to add this idea of a null value. That's what I think I'll do. So I'm going to say let ret equal the length, and then I'm going to say I've got to add this to the end, which is annoying. So set, then I need to give it a value for the memory. So that's going to be mem plus plus null. So I've stuck a null into memory, and then I'm going to return ret. So that's going to return an index to the memory we just allocated, if you like. And then finally, we need a few more things in our abstract syntax. We probably want sequence. So sec, and that's going to take expression. So that just says do one expression, then another expression. We're really in the land of imperative now. And then I'm also going to want assign. I don't have an assignment yet. So that takes an expression and expression. So sec's nice and easy. Eval sec e1 e2 env equals really nice and easy. It's eval e1 env, and then we ignore the output. So that would mean take this monad and stick it into the next function. But if we don't have the equals at the end, it means sort of calculate how it changes the monad and ignore the value and then run the next function, which is a monad, if you like. So that's going to be eval e2 env. So that's sequence done. And then eval assign e1 and e2. I don't know if it's meant to be two expressions, but I think so. So this is kind of the colon equals. So how do I want this to work? So I think I want to evaluate the first one into, I'm thinking hard about how I want this to work. You see, making interpreters is a very creative endeavor. Well, either way, I'm going to be evaluating some stuff. So I'm going to do it in this for now. So E1 prime is just going to be eval E1 env. E2 prime is going to be eval E2 env. And then I'm going to want to actually do something now. So I guess I need E1 to be... So how do I want this? Because I don't have an idea. So I guess whatever I want this to evaluate to a num val. So because that's my index, if you like. What would actually be a lot more helpful, actually, is if I had num val and sort of I'm going to add another thing to my value. So I've got a num val, but I'm also going to have mem adjur, and that's also an integer. It's basically the same, but I'm going to differentiate between them. So I'm going to change what I did here, and that's going to be mem address instead, and this is also going to be mem address instead. New. Oh, good thing I checked my work. Mem address ret. No, let's remove those brackets. Okay, and so back here, so I've evaluated E1 to a memory address, and I want to change whatever's in there. So it's going to be, mem is going to be get, I'm going to get the memory, and we need to change the ith element in memory. There's like no good way of doing this in Haskell really, which is irritating, because this isn't a vector, where I can just say replace in the vector library. You can do this I don't know. I mean, it's on still, but it's nicer anyway. So mem prime is gonna be take the first I elements, add in E2 prime, and then drop the first I elements. Oh, I need mem in these two places. So I think that works. So say I had 1, 2, 3, that's my memory, and I said, and my address was 1, then it would take one element, so I end up with 1. I'm replacing it with a 5, say, and then I drop one element. No, sorry, that needs to be +1. So far that was an insert. Okay, cool. And now we need to set the memory. So set mem, we're using set now, and finally, this is a long one, we need to return something, so I'm just going to return null. Okay, so I think we've added new deref second assign. What can go wrong? Typos can go wrong. So that's line 107. E2. Well, hey, look at that. You see, when you add monads, things get so much easier. But now is for the hard part, which is working in abstract syntax, which someone in the comments reminded me is essentially Lisp. Lisp is so difficult. And we need to test this out. So let E equal... So I'm starting with sec. So this is already going to be horrible. So the first thing I'm going to do is I'm going to let, and then it's going to be val, give it a name. Yeah, okay, I've got this. I've got a good way of explaining this. So let val x equal new in, and I'm going to say assign, and then it's going to be var x. Is it var x? So I think so. And I'm going to say that equals num val 42. Okay, so that's one side of things. So let val, so I need to put more brackets in. Okay, so couldn't match type expression of actual type value in the second part of assign. Oh, it's number. Okay, so E, whoops, I meant the type of E is expression to expression. Okay, so I've got sec. So what I've done is I've done something like this. I've gone let x equal new in x assigned to 42. That's like my first statement. And now in my second statement, which if you remember in the code, the environment hasn't changed. The environment is back at this point, just like it was at this point. Okay, so x, we've kind of lost x now. Actually, that is problematic. So I need to refer to x now. Oh, maybe I need to do. No, okay. Change your plan. Change your plan. We're not going to use sec there. Because I need to be able to. So, okay. So we've assigned x to 42. What I'll then do. Okay, so put some brackets here now. So I'm going to have a sec here. So the first thing I've done is, where does that bracket? So that's 1, 2, 1, 2 here. So I've assigned x to 42. I'm then going to add 1 to that. So I'm going to say plus, and then it's going to be no, hold on. So it's going to be an assign, and on the first side it's going to be x, so var x. So x is going to equal, and now here it's going to be plus, and then I need to deref, and then the variable x, and then number 1, always make that mistake. So x equals x plus 1. Let's just see if that errored. It didn't error. So let res equal eval e in the empty environment, and then if I go run state res with nothing in the memory, oh, there we go, 43. So the problem was I had Yeah. I'd just set the original memory back instead of mem prime. Oh, Haskell doesn't get rid of your bugs. It just makes them less likely. But okay, that's all for this tutorial. We've successfully managed to add memory to our interpreter. We've made an imperative interpreter now. So next tutorial, I'm going to talk about adding lexes and parsers to this all. So it's going to be a bit of a new one. Okay, thank you so much for listening, and see you next time.